新的学生非常没有成功，您的儿子是就今年就下半年上大学，去上个学期他就跟着那个 UT 那帮人去，然后呢就介绍这个是我们的 engineer school， 然后呢这个撞那个马姓 robot。
Good morning. Welcome to the 54th Lunar and Planetary Science Conference. We're glad to see how many people are coming to today's plenary town hall for Mars sample return. Honored this morning to host. I'm Eileen Stansberry with the Chief Scientist at Johnson Space Center, with my colleague Lisa Gaddis, the Director of the Lunar and Planetary Institute. And we have with us a number of esteemed colleagues from the Mars Sample Return Program and the Mars Exploration Program. And I'd like to, rather than describing the list of everyone who's on here, who will be providing support today, I'd like to first introduce Jeff Gramling, the Director of the Mars Sample Return Program from headquarters, who is going to start the briefing. Jeff, thank you very much.
Thank you, Eileen, and we're happy to be here this morning with you to talk about what's going on with Mars sample returns. We've got a whole group of people that are going to talk to you about what's going on in the program, what's been going on with Perseverance and the samples we've been collecting, and then we recently have stood up the Mars sample receiving projects. We've got people who are going to tell you about what's going on that part of the program. All right, so I'm sure you've all been following what's happened. We just this January, the caches or the samples that Perseverance has been collecting, and there's quite a diversity of samples, and you're going to hear about that. They were judged to represent a return-worthy set. The Perseverance team that Ken is going to tell you about successfully completed putting down the first surface cache. And what that does is it gives us mission resiliency. In other words, if anything happens with Perseverance going forward, then we've got this cache to go and bring back. And we're very excited about that. And I'm sure Ken's going to explain the fact that we've been double sampling up until that time and what he and the science team are planning to do going forward. Let's see what we're doing. We're in phase B. We entered phase B at the beginning of October last year. In phase B, that's the last phase of formulation. It ends with our preliminary design reviews. And I think you're all familiar with the elements, the major elements of the program, which is the sample retrieval lander that's being built at JPL, the capture containment return system that's being built at Goddard, that's the payload on ESA's Earth Return Orbiter, and then the Mars Ascent Vehicle that's being built by Marshall Space Flight Center. So each of those are working to get to their PDRs. And then once that's done, it will be followed by a program or system level PDR, and that will happen before we ultimately go to the agency's decision to confirm the program and put us into the implementation phase. I think if you've been following what's been going on, we've been doing quite a bit of engineering concept validation testing among just a few of those I'll talk about last year we did drop test of our Earth entry vehicle in a similar type of soil as we'll see in the desert in Utah. We're in our planned landing site, so that helped us validate that we've got a design that's going to protect the samples when we land. The other thing, I'm sure you all remember that at one point we were looking at the possibility of needing 2 landers, one to land the Mars Ascent vehicle and another to land the Sample Fetch rover. About a little less than a year ago, we made the decision to go with a 1 lander architecture. We de-scoped the sample retrieval rover, and instead we are flying 2 helicopters on the 1 lander, and those would be how we would go and get samples that are cached on the surface. Again, the primary plan is that Perseverance will remain healthy and be able to bring us the full sample set that consists of not only the samples that have been taken to date, but the samples that Ken's team will continue to collect going forward. All right, the one thing about our architecture, we've got a lot of engineering complexity, we've got organizational complexity. The one, what we don't have a lot of technology development. It's mainly in the engineering complexity. We're on track to get to our internal requirement, which is TRL, or Technology Readiness Level 6, by our PDR phase. Kind of one of the last main things that we're looking to do here in the next month or so is to complete a test firing of our demonstration motor 1. That's a solid rocket phase or stage of the Mars Ascent vehicle. So that's coming up in the next month or so, and that will complete a lot of they'll get us to the technology readiness level we need to be at for our PDR. So let's talk a little bit more about the helicopters. So I think you've all been following the successful flights of Ingenuity on Perseverance. We're taking that design and we're augmenting it to serve the purpose we need. The main augmentations are adding a gripper to be able to carry it, pick up a tube and carry it, and ground mobility or wheels so that we can land next to the tube and then drive over it so that we're in the position to grab it and then fly it back to our lander. We've been doing testing in the chamber. Basically, those augmentations bring mass growth, and we've been doing testing of an engineering model of Ingenuity in a chamber simulating the pressure on the surface of Mars to validate what we've got to do to make sure we've got both lift and controllability. So we're making good progress there. Again, though that was a kind of a late addition, so we're trying to catch up with where we're at with the helicopter development, but we're making good progress. Independent review board. So besides our normal process of our preliminary design reviews, and remember those are all chaired by independent organizations, our system level program, our PDR was chaired by the agency's standing review board, chaired by Dr. Maria Zuber. We've decided that because of the complexity of this program that we're going to stand up another independent review board before we proceed to our system level PDR, and I'll show you the timeline coming up. We expect that independent review will take about 6 to 8 weeks. So in the process of standing that up, we think that's the right thing to do here before we finalize our architecture and move into implementation phase. Go on. All right, we're happy with the President's budget request. It funds the program to continue to do the work that's necessary to get to our targeted launch dates as early as 27 for ERO and CCRS and 2028 for the sample retrieval lander. And again, going forward, we're in the process of finalizing our grassroots cost and schedule estimates for each of the elements. Those will be reviewed by our independent review boards and the IRB. In addition, we will do independent cost and schedule assessments before we go to agency confirmation, just as we did for KDP-B. So that's coming up. All right, our path to confirmation, then the current schedule is our European colleagues are actually completed their PDR for the Earth Return Orbiter back in June of 21. So they're out in front of us. That's being built by Airbus in Toulouse. Our sample transfer arm is also a European contribution. They conducted their PDR back in November of last year. We're working to get to part 2 of our PDR for the capture, containment, and return system. We hope to, we believe we're on track to do that in June of this year. Sample recovery helicopter, again, they're a little bit behind us, but they're making good progress. We had a systems requirement review back in February 2020, and we're working to continue to mature that design to catch it up with the rest of the system. Mars Ascent Vehicle PDRs coming up in April, not too far down the road, followed by the sample retrieval lander at JPL. And then as I mentioned, we're planning for 6 to 8 week independent review board, and that will take place in the May to July timeframe. And then we would follow that with a system level PDR and then agency confirmation, hopefully in the early part of fiscal year 24, which means the October timeframe. And I think that's all I have for you. And I'm going to let Dr. Wadwa come up and talk to you about what's going on with sampling and where we're at. Thank you.
All right, it's great to see everybody here. I'm super excited here to tell you a little bit about where we are in terms of Mars Sample Return Program, and especially in terms of the samples that have already been deployed in the first depot. This picture, and this is, I think, the 3rd or the 4th time that I've actually seen this picture at this meeting, but I think it deserves that attention because it truly represents a historic achievement. First time that we've had a deployment of a suite of samples on the surface of another planetary body ready to be brought back. And this is just incredible. And so to me, it's just super exciting that we are at a point now where we are we're within about 10 years of bringing samples back from Mars. Woohoo, yes. Yeah, so this is a really beautiful, beautiful picture of these 10 samples. And what you see here, and this is, again, I'm sure you've probably seen this slide as well during this week, but there's a lot of information on this slide. This is basically the family portrait of all of the samples that have been collected so far by Perseverance. And what I'm showing here, let's see, are these horizontal strips. If you're not familiar with this, basically we've got 3 to a strip for the most part, with the exception of a couple. And essentially, all of these pictures of this rocks are superimposed on a map there that you see of the locality where Perseverance has been exploring Jezero Crater and the Delta Front and collecting these samples, and the red dots are the locations of each of those samples. And you can see the lines then to each of the rocks that have been collected. And on the left-hand side, outlined in the red, are the abrasion patches. So these are about 5 centimeters across. Abrasion patches on individual rocks that have been collected, with the exception, of course, on the top left is the regolith sample. And you also see that next to that are 2 pictures. And so Jeff mentioned that we've been taking this paired sampling strategy for each of the samples that have been collected within the Jezero crater region up to this point. And that was deliberately done because the plan was always to put one of the pair in the Three Forks depot and carry the other one, and actually the better one, on board Perseverance, so that those could then be further, I guess, that the cache that's on board Perseverance will only get better with time as Perseverance continues to explore the crater rim and beyond and collect more samples. The plan is to bring back as many as 30 samples eventually. And so Perseverance is the prime pathway for doing that. And in the meantime, though, as Jeff mentioned, we are trying to be as resilient as possible. And in the case of some kind of contingency, we are able to, of course, bring back the samples that we're going to be depositing or that we have already deposited at the Three Forks Depot. And so what you see here are, what really pops out at you is the incredible diversity of the samples that we've already collected. And as you see in some of the, I don't know if I have a pointer here. Yeah. The boxes that are outlined in green are the 10 samples that have been deployed at the Three Forks Depot, which is somewhere located right around here. And there are a variety. There are basically 7 rock cores, of which 4 are igneous rocks. And you can see some of them down here, as well as this one right over here. And these ones are, again, there's some basaltic materials there, pyroxene plagioclase basalts, as well as olivine cumulates. And they also contain some amount of alteration, some salts, carbonates, sulfates, and represent some degree of aqueous alteration. So you're seeing actually a wonderful history, magmatic history, as well as history of water on that planet that's recorded in these igneous materials. And we're going to be able to date some of these samples and be able to anchor the timeline for the crater chronology calibration for Mars as well. So that would be super important. In addition to that, we've got 3 of the cores that are sedimentary rocks, and these are represented here. Among them, we've got samples that are extremely fine-grained, that are mudstones or siltstones that have a lot of cements, sulfate cements, very strong fluorescence, which could indicate that they may be organics, but that's something that's being verified at this point. Then there are other somewhat more coarser grained sandstones. This one here is a sandstone siltstone and has actually some zircons and bedellites as well that are going to be datable materials. And then, of course, we've got an atmospheric sample, which was a serendipitous atmosphere sample. This was the very first sample that was tried. We tried to sample that, and the basalt was just too crumbly. And we sealed the tube without actually having the sample in there. So that's our atmospheric sample. And there's a witness sample as well. That's going to help us to constrain some of the potential contamination that might be present. This sample, of course, is another core. That's a singleton that was collected. And that's going to be just carried on board Perseverance as it moves out beyond Jezero. So beautiful samples that are going to address a number of the high priority science goals for Mars sample return, including, as I mentioned, igneous materials to give us absolute dates to anchor the ages of Martian epochs, sedimentary rocks from the delta front that will help us to ascertain whether there's evidence of past life. In fact, these samples are our best prospects for being able to answer the age-old question of whether life arose elsewhere in the solar system and beyond. Aqueous alteration products to understand the history of water, likely presence of organics, possible presence of organics that of course we'll be able to analyze in labs here to determine whether they may be biogenic or abiogenic. And of course, these samples will also support future human exploration as well. So hope you're as excited about all of the prospects of bringing these types of materials back. And as I mentioned, Perseverance is only going to be improving the cache on board, and that's the cache that we hope to bring back. And with that, I'm going to pass this along to Ken Farley, who's the project scientist for Mars 2020. And oh, by the way, yes, there are lots of these wonderful stickers out front. Please take them and definitely spread the love. All right.
So as Minnie said, I'm project scientist for the Perseverance mission. And before I tell you what is ahead of us for Perseverance that is going to feed into MSR, I want to let everybody know, if you don't already know this, the samples that we've collected so far that have been put down in this first cache have been very carefully documented in a series of documents we call the initial reports. We just put into the PDS. I'm not sure it's gone public yet, but it will go public soon if it hasn't. The next 240 pages documenting the samples that we collected on the delta front. We already had the crater floor samples there. So if you're interested in the samples, there is a very detailed set of narrative description of the samples. It's not just a random collection of data. It is a narrative description of each and every sample. So my goal here, if I can have the next slide, is just to tell you a little bit about what, I can control. What Perseverance is going to be doing going forward. So as Minnie said, we are no longer double sampling. We are done with that phase. We are not preparing to deploy another cache. We're just single sampling. And we have 23 tubes on board. So I want to tell you what we're going to be doing between now and when we make the rendezvous with the MSR missions. This is a very recent image from the current area that we have passed through just within the last few sols. These are really spectacular cross sections of river deposits. So this mission has turned out to go through a series of what we call campaigns. First campaign was on the crater floor where we found igneous rocks. Second campaign was on the delta front where we essentially got a cross section of the sedimentary rocks deposited in the lake and in the river system that filled the lake. And now we've driven up on top of the fan where we are seeing what we believe to be fluvial deposits, river deposits. So this, what we call the upper fan campaign, is expected to last until the middle of October or so, depending on what exactly we find. And the goal here is to explore, characterize, interpret, and sample rocks deposited on the top of this feature, what I think to be mostly fluvial. And we expect to collect during this campaign more sandstones. We collected sandstones low down in the section. These will be sandstones from higher up in the section and may represent different provenance, different grain size. Conglomerates, each and every grain in a sandstone or a conglomerate represents a rock that has been brought from somewhere else. That's very exciting. And we are also looking for hydrated silica. There's reason to believe that there is a hydrated silica deposit based on orbital data from CRISM, which would be very interesting from a biosignature preservation point of view. Also looking for sedimentary rocks with clay-sized grains. These are important for organic concentration and preservation. And we may also find either hydrothermal or diagenetic features of both general scientific interest, but also from an astrobiological point of view. And one of the things that I think will be really interesting is we are going to start seeing what I call here exotic boulders. These are boulders brought from up in the headwaters. These are not little tiny things. These are big boulders. And so potentially every one of those is a piece of Mars that we may or may not see in our future. So we'll spend some time looking at those and we may choose to sample them if they look especially interesting. So that's the upper fan campaign. After that, we move into the region called the crater margin. You can see just texturally the area labeled crater margin looks different. This is a carbonate and olivine rich area, and it may be a deposit produced in the lake. The carbonate may actually be lacustrine. That would be a wonderful discovery. But this is the area that we will explore next, probably through about spring of next year. And we will likely collect olivine and carbonate, which may be sedimentary. It may also be igneous. It may be similar to the crater floor rocks. And we will reach the inner rim of Jezero crater and start looking for rocks that have been brought up by the Jezero impact itself. And they may also, in association with that impact, be hydrothermally altered. So we're acquiring yet a different set of samples once we get up there. And then finally, in the out years, the plan is that we will move out of Jezero crater, move up the crater rim onto the Nili-Planum area, the highlands surrounding the crater, where we will discover completely different geology, where we find different geology than exists in the crater. The pre-impact crust, there may be hydrothermal systems associated with the Jezero impact up there. There is likely to be megabreccia, large blocks of deep crustal rock brought up by either Jezero or, even more interestingly, from Isidis, the giant impact basin, not too far off from Jezero crater. Phyllosilicates, olivine and olivine carbonate. So again, a big diversity of samples to be acquired through something like 2030 for when the rendezvous happens. In that time, we will also survey, validate the landing site for MSR, deliver the baseline cache to the sample retrieval lander. So that is the plan forward. And I think now I turn it over to Michael Meyer, who will tell you more about scientific aspects of this.
Yeah, so one of the things I want to talk about is science is the one thing that's going across two separate programs for Mars sample return. So the Mars sample return campaign, what connects it is to science. And so what I want to point out a little bit is what we're doing to protect that science as we go forward and what we've been doing in the past. So one of the things is over this last year is that we established the Mars sample return campaign science group. You'll recognize many of the people on here. Essentially, the terms of reference were signed last March. And then basically we stood up the group, got them going and meeting by June of that year. And so their focus is looking at how we're going to look at the campaign science, maintaining recommendations for maintaining sample integrity, and looking forward to what kind of ground-based infrastructure we'll need for receiving those samples, and in particular, making sure the science community is engaged in this whole process. And I want to point out that these people were selected as an open competition. We sent a letter out to the community saying, please apply. And then basically NASA and ESA got together and went through and selected these august membership to help us to go forward. There's two phases. One is the one I just mentioned that we're in. The second one is based on, this group operates kind of like a project science group. And so the second phase is when we actually have instrument investigation competitions for what may be going inside a sample receiving facility. And those people will be, that are selected will end up being members of the campaign science group and help us go forward as we're planning what the science challenges are as we recover the samples, build a facility, and set up for analyzing them. And just as a note, this is something I kind of learned. I should have known this a long time ago. We signed a science MOU with ESA, and this is actually our only legally binding document for that's concerning the science for this program. So that's kind of good on a programmatic sense. So what has been happening? One of the first things that the campaign science group did was, in fact, organize a scientific community meeting, which was to look at the samples that were being planned to put into in the Three Forks area that we just heard about. And as we see, there's a marvelous set of samples. And then kind of looked at it and made, you know, what is our rule structure for which samples to put in on the surface of Mars versus those that remained inside the rover. We just had a meeting this past February where we went through and discussed a lot of the issues that are coming forward as we go forward, particularly with the establishment of the sample receiving project. And this is the kind of things that we need to have in terms of how we're going to do, prepare for the concept, the mission concept review that's going to happen this summer, looking at the instruments that actually go in the facility. One of the things we talked about is having a measurement definition team. I'll talk a little bit more about that. And some of the other challenges, like how do we get the samples out of the tubes, et cetera. So the next opportunity for the science community is, in fact, we're going to have a measurement definition team set up to help guide us in terms of what will go inside a sample receiving facility. So the samples have to be in containment until they're shown to be safe. And also we need to keep those samples pristine because we want to do the science that we want to do and making sure that we know what is Martian versus what might have been Earth contamination. So that team we're going to set up soon. I put this in here. There's a URL. If you are interested, please put your name in because as soon as we get this set up, it's going to be a pretty rapid turnaround. And so you don't want to be on vacation and miss the opportunity because you didn't hear about it in time. So put your name in there and we'll notify anybody that's on there besides a broadcast of what is needed, how do you apply. It's probably a couple letter kind of thing saying this is why I'm a great person to be on the measurement definition team. So we're going forward with that. So one other thing that's kind of affecting the science, or actually we're trying to help preserve the science and integrity, is we have a challenge of we're bringing the samples inside of us from Mars to Earth, and we have to break the chain of contact. In other words, we can't bring back Martian material that's not contained. or sterilize. And so the process we were using was getting too complicated, and also we're worried about the way we're sealing the os or the primary container may raise the temperatures on the samples and may jeopardize the samples we're trying to bring back. So what we've done is change the approach to planetary protection. We are looking at realizing that the threat from subcellular components, things like prions and that kind of thing, on the outside of the os, the dust, what we're worried about is the dust that might be associated with the os, which is like 200 milligrams, like 1/250th of a teaspoon. This is what we have to concern ourselves with. So the idea is we're not worried about the subcellular component because of the sheer numbers of it. And then any particular, let's say Martians that are hitchhiking with the dust itself, we're going to go through a sterilization process. This is a little bit different than we planned originally. And to make sure we're on the right tack, the Office of the Chief Scientist has set up a panel to review what we're planning to do and render some finding in terms of what our approach is and what experiments we need to do. We're starting some of the experiments now to make sure that we're on the right track, making sure that we're breaking the chain of contact between what's on Mars and what comes back to Earth. And that way, all the samples, all the things that we're concerned about for the science itself are contained within the OS. And with that, I would like to introduce Tiffany Morgan, who's the Deputy Director of the Mars Exploration Program, and also in this role as the Acting Program Executive. Thanks.
Thanks, Michael. Good afternoon. So on to the final component, onto the final component of the Mars Sample Return Campaign is the Sample Receiving Project. And this is a unique project because it's a joint collaboration between ESA and NASA, where our scientists and our curators are working side by side, integrated in developing the requirements for the facilities, for the recovery, in determining curation and scientific objectives. I'm going to walk you through a chronology of what awaits the samples when they return to Earth. I think Jeff mentioned earlier a drop test, the Earth Entry System drop test. You can see a picture of that in the bottom right here. The samples will be released from the Earth Return Orbiter, and they will enter Earth's atmosphere contained in the Earth Entry System, and they will land passively in the Utah desert, the Utah Test and Training Range. And that's without a parachute, hard lander. And what you see here in this picture is the test article, near life-size test article. As soon as those samples touch down at the Utah Test Range, the Sample Receiving Project will take control and responsibility for those samples. They will bag them and put them in a box for containment and planetary protection purposes. And then they will transport it to a staging area where they will further contain it into a mobile vault, and then it will get transported to the sample receiving facility. So once we get into the sample receiving facility, we will de-integrate the samples from the Earth Entry System, which will then analyze and catalog all the information from that for contamination control knowledge in the future. One of the key goals of the Sample Receiving Project is to enable safe and rapid release of these return samples to worldwide laboratories. We want to be able to get these samples out to the best scientists in the world at the best laboratories to enable phenomenal scientific discoveries within these samples. But to do that, there's a handful of things that have to happen first. We need to do the sample safety assessment, curation activities, and objective-driven science. That is all going to be accomplished early on. Some of this is going to be accomplished early on before release as part of basic characterization, preliminary examination. There will be two ways to begin to release these samples. The first is an option to sterilize the samples because they have to be safe. These samples come from the Mars Sample Return Campaign, which is a planetary protection Category 5 restricted Earth return mission. So to be able to release these, we need to make sure they're safe for the environment. The last time that happened was with the Apollo samples over 50 years ago. So we'll open the tubes, we'll have an option to sterilize those and get those sent out right away, but we're also going to continue to do time-sensitive, objective-driven science and those curation activities of the unsterilized samples. And so after we've gotten through a process that would enable us to release those, they will leave the containment facility and go to other laboratories, like I mentioned before, around the world, and that will occur outside of containment. That will primarily be for objective-driven science. However, we're also considering and planning on opportunistic science, which is discovery responsive science, not just science investigations to meet the objectives of the sample receiving project. So what we have here are draft science objectives. Within the facility, in the contained facility that is jointly managed by ESA and NASA within the US. After they're released, they'll go all over the world to accomplish science from the samples in Jezero crater. And you can see here, there's a little green dot or a little green circle. That's where the surface cache is now. These draft science objectives, if you look at them at first look, might sound like some of our other missions, our landed missions, but the big difference here is that we'll be able to do this on Earth, right? We'll have high precision, high accuracy sample studies, and we'll be able to have multiple instruments of the high precision, high quality to look at these. We'll be able to make amazing discoveries here on Earth with the samples. And then from a programmatic perspective, we've got two schedules here. This is our high level schedule. It's notional. This is, we are still in the pre-formulation phase for the sample receiving project, but you can see we're going to continue sample collection. They'll make their return trip to Earth. We'll begin measurements at some point in time during doing those measurements. They will be released, and then there'll also be long-term curation. But to get ready for the samples to come back, we have a lot of project activities to accomplish over the next 10 or 11 years. We're doing feasibility studies on the sample receiving facility right now, and requirements and design phase will start in the near future to get us through to a site-specific design for the facility, as well as for our recovery activities and for the vaults and for anything for containment. In parallel, we'll have our NEPA environmental impact study, and then we'll begin development and construction of the facility, and then ops readiness. You commission the facility, test, train, and have an operational readiness review for both the facility and the recovery operations. And then we'll have containment operations, and that'll get us into 2035. So just before the end of last year, we formally established a sample receiving project office at Johnson, and they have selected a new project manager, Dr. Alvin Smith. He's been on the job for 4 days now. So we're going to bring him up here to talk about a few more details of the project. So Alvin, Dr. Smith, please.
How awesome is this on day 4 to be here with you all, right? So that's pretty cool. So I'm super excited to talk about the next step here, and really the MSR and the SRF and what this sample receiving facility is really going to be about. So when we think about, and as you heard, all of the care and steps that are taken into collecting the samples, but also making sure that we're protecting the integrity of the science bringing back, we want to make sure that we continue that process all the way through into the SRF and how we think about understanding the characteristics and the science and everything behind that. And so when we think about this facility, it's going to be one of a kind. It's going to be something that we've not done before. So there's going to be lots of firsts. And so when we think about these high containment, as was mentioned before by Michael Meyer, with regard to making sure it's high containment, and we're looking at facilities like BSL-4 or biosafety level 4, like or equivalent, that's going to satisfy that backward PP element of making sure that we're keeping the samples safe from that planetary protection standpoint as it goes forward and backward. We also want to make sure that that is a pristine environment. So now we're talking about really combining two technologies that really have not been done before. So when we think about planetary protection or BSL-4, that's negative pressure, right? So negative pressure facilities, we all may be very associate or understand clean rooms that are positive pressure. So now with this negative pressure containment space, and also now merging this clean environment that must be positive, really I'm trying to understand those really competing pressures. That's going to be something that we really need to get into. And that's going to be one of the really sticking point and really the one of a kind like features of this facility. We think about, again, how do we get the samples out fast enough, right? That's really going to be critical. We don't want these samples, and we certainly want folks to understand that it is our goal to release the samples from this facility as quickly as possible. So it's not our business to have these samples and they go into a black hole that folks never see again, right? We want to get them out to the community, to you, to be able to truly operate and truly understand really the significance of these samples. So again, I mentioned the strategy here and really dealing with those positive and negative pressures, and that's something really that is going to be a key paramount issue here. So we've just had, and as Tiffany mentioned, there was a sample, a Mars sample receiving planning or a assessment study we called MSAS. And this helped us look at some of the modalities which could be effective in allowing us to really build a facility. So we looked at 4 different, one is really looking at existing. We know that there are BSL-4 buildings around the world and certainly within the US. We know that there are also clean room labs as well. And so we looked at what existing technology already exists. Can we fit our science goals and those instruments and everything into this new facility? We also looked at, well, if we need to build a traditional building that is this brick and mortar, which is traditionally how it's done in the US, can we do that? Then we looked at this other called a modular or a volumetric, which is something that we've seen implemented for other laboratories and new other science buildings. Now, this is something that's been tried and tested at a BSL-3, so a little bit lower than what we may need, but we know that the technology works and we're investigating that as well. And we're looking at ways, how do we take that, our understanding of that, and then understand that for BSL-4. So we have some folks that are looking at that. And then lastly, taking in the hybrid approach, if we take an existing or a traditional build, which is our brick and mortar, combining that with this new volumetric approach, what does that also give us as far as being able to meet those capabilities and also our schedule? So we've been looking at that, and so we've actually just wrapped that up. There we go, did I miss one? Okay, I guess that was the last slide there. I thought there was one more after that. See, there you go, day 4, right? But so with that, we do have some results, and we're working on that with my team. I'm so excited to have a great team to help me kind of, step through that. And so you'll see some of that. There will be an RFI that will be coming out, a request for information from the community to understand what infrastructure, whether it's BSL-4 or BSL-3, that already exists that we may want to leverage. So with that, I'll stop there and I'll pass this, I believe, back over to Jeff Grambling, who will wrap us all up. But please look forward to that RFI and other information for SRP. And so happy to, this is my first LPSC, so thank you.
All right, thank you, Alvin. So this is the last chart and we'll wrap it up. So just to bring this all back, we've given you a lot of information today, and hopefully you can see where a lot of progress has been made, and we're on the program, we're wrapping up our formulation phase and working towards our agency confirmation. Of course, MSR continues to be a challenging and complex mission. You've kind of gotten a sense for all of the elements that are involved. bringing back scientifically selected samples from the surface of Mars safely and satisfying the back planetary protection requirements. And you know, beyond just the value of the samples themselves, as I think Michael mentioned, you know, what we're doing is going to lay the groundwork for safe human exploration of Mars someday in the future. How we're implementing this complex mission is we've got a whole bunch of the agency involved in this across many field centers. You've heard from several of us today. I mentioned where the other work's going on, and even for the centers that aren't building hardware in-house, we're employing them for subject matter expertise, and that includes Ames and Langley, and the Ames folks are also helping us out with the helicopter work. And of course, several industry partners and our European colleagues with building the ERO and the sample transfer arm. And as you just heard, just recently, we've stood up the sample receiving project. So work has started there in terms of how we're going to recover and then ensure the samples are safe before we put them out for study in labs around the planet. Just a few other comments and then we'll take questions. For those of you that have seen the sticker, this is actually the shape of the orbiting sample container. So that's what that means. And Lori reminds me, we didn't really have time to do it today because we had so much we wanted to share with you, but there's a really neat animation we've done of the current concept that's out on our website, which is at mars.nasa.gov. So I encourage you, if you haven't seen it yet, to go take a look. It's pretty well done. And with that, I think we're going to have all of the speakers come up and we're happy to take questions.
Please remember to state your name and affiliation as you're asking a question. Go ahead.
Hi, Allie Fox, Texas State University. I'm wondering if you can clarify the sterilization procedures given the importance of the astrobiological significance of these samples. Particularly, is that the measurement definition team that will be deciding what types of techniques will be done prior to sterilization, and also who is making the final decision on sterilization overall? Thank you.
Let's see if this works this way. Oh, there we go. Yeah, the measurement definition team, what they're actually going to do is kind of verify what we think are the science objectives. So it's something that needs to be accomplished in the first, years of the project when the samples come back. And they'll go through developing what measurements are needed, how that translates into what instruments are required to be within the sample receiving facility, and then back that out into what measurements are needed. Those will end up being your level 1, 2 requirements for the sample receiving facility. So that's kind of what the process is, and what it is, because we have to all work together on this. The measurement definition team will say, this is what are the requirements. There may be a debate about whether or not those can be accomplished. And, how do you, it's sort of like the same thing as selecting instruments on a spacecraft, where you might have to make compromises in order for everything to work.
Yeah, Chris Hurd, University of Alberta. I have a question about, for NASA headquarters folks, just wondering about, there's a lot of expertise out there in the community that relates to sample handling and curation methods. Is there a funding envelope or plans for that to be able to fund research done in the community in preparation? Because there's a lot of work we got to do between now and 2033.
Yeah, okay. So we're still pre-formulation, so your feedback is well received, and I think we will take that into account. And we're still working on putting together our life cycle budget, but we do have research and development tasks that are pre-programmed in and definition of those. Like I said, thanks for your feedback. We'll take that into account.
Bernard Frank, CEO of Europe on Mars, but also the Vice Chair of the COSPAR Planetary Commission and Exploration Panel. So I have a question about how we could also validate some of the measurement definition aspect, sample characterization, protocol for receiving facilities on the moon, for instance, taking some synergy with what is going to be in place in the lunar program, or also on extreme terrestrial analog on Earth. So are there some plans to conduct eventually some validation of some of this instrumentation on extreme desert or also on the moon?
I have to admit, Bernard, I didn't fully get the question because I couldn't see your lips.
Yeah, you have a measurement definition team and you have a protocol for sample acquisition, characterization, and receiving facility. So could we make use of an early demonstration of some of this instrument in a precursor mission on the moon, or also mission to terrestrial analogs?
Okay, so instrumentation on the moon, I'm not sure if that would be particularly helpful because the instruments that we want to use are instruments that we can't send on a mission. But certainly back here, we are already considering analog programs, not only in terms of the samples themselves and their physical properties, but also the nature of the samples and, you know, okay, how are you going to do carbonates and that sort of thing. And so as we go forward, when we start, you know, say narrowing down what instruments we're specifically going to use, there is certainly going to be an analog program to make sure that we have everything down so that when the samples arrive, we don't have to guess anymore about how to treat everything.
Okay, Amanda Hendricks, Planetary Science Institute. I've got a couple quick questions. First about MSRF. That schedule looks really tight in terms of getting it built by the time the samples are ready to be put into it. When, I wasn't clear on when a decision is going to be made on where that's actually going to be on the planet. And then my other question has to do with this second IRB, whether that's been populated and who's going to chair it.
Okay, I can address the question on location first. So we just finished one aspect of the study for modality that Dr. Smith spoke about. The next step is there's an RFI coming out. So we're waiting for the RFI information. And then we're going to do a second phase of the study for site specific. The NEPA environmental impact statement will factor into that. And I think it's about a year out, a year to a year and a half. And a lot of these things are going to happen in parallel. So we're looking at options for doing facility design, not site-specific design, in parallel with determining what site it specifically will be. But there are still a handful of options on the table. So a year and a half to 2 years.
Before an actual site is selected.
Correct.
Got it. Thanks. They haven't. Oh.
All right, your second question was about the IRB. So we're in the process of last week, we began, reaching out to people and trying to populate the team. So that's in work.
Okay, great. Thank you.
Sorry, we have a question online. Pooja from University of Nevada, Reno. How much emphasis is put on prioritizing non-destructive methods over those that will destroy the sample? For example, if our science objectives that are a certain way, emphasizing a certain goal, such as biosignatures and isotopes, there might not be enough samples to go around, as all those objectives require samples to be destroyed to gain accurate and high resolution data. So is the group seriously considering all those things?
So I think there is definitely an emphasis on trying to maximize the science from the samples. And so, this is going to be a limited sample set. But, fortunately, in the sample science community, we've had a lot of practice trying to maximize the science from very, very limited amounts of samples. We've had things like stardust material that have come back with literally tiny little grains that we've really got some amazing science from. And lots of examples like that. And so I think, we've already developed the capabilities to do a lot of the kinds of coordinated analyses that are needed, sequential analyses that are needed, where you get the most out of a given small subset of sample. So that's definitely going to be a priority. But yeah, recognizing that some of the types of analyses that we would want to do, for example, like dating the samples, I mean, that's going to require some amount of sample, destructive analyses.
Yeah, and added to that, some of the samples are going to be put away, or subsamples, I put it that way, will be put away for future generations to analyze, similar to what we're doing with the Apollo samples now.
Tracy, hang on, please. Are there questions in Waterway 5? Questions in Waterway 6? Tracy.
Tracy Gregg, University at Buffalo. Given the small amount and the preciousness of these samples, are there plans, I hope, to set aside some for educational resources like has been done for the lunar samples?
Yeah, so again, we're still working out the logistics here on that. But again, as Michael mentioned, with regard to understanding how we want to get samples out and also reserve some samples for future use, just like we've done very recently, absolutely, right? So I think these are things that we're considering. What those percentages are and how we do that, again, we've just started to tease that apart, so.
Thank you. I think the taxpayers who actually funded this mission should be able to see the samples eventually.
I completely agree. Yep.
Hi, Louise Proctor from the Applied Physics Lab in Maryland. Thank you. Great presentation, really exciting mission. I have a question for Jeff Gramlin. So you noted you were very happy with the NASA budget. But there was also language in the budget that proposed delaying a heliophysics mission to help pay for Mars sample return, at least one in GDC. So obviously this is pretty concerning, should be concerning to all of us. And I'm happy to see that you're standing up an IRB and you've already undertaken some descopes. But I have two questions. One is, are you willing or able to give us even a ballpark cost at the moment? You didn't mention that, and I know you're undergoing analyses at the moment. So we appreciate that it wouldn't be set in stone. It's very rough and probably would be an underestimate. And then secondly, can you speak to whether you feel that we now have a pretty solid understanding of the scope of the project moving forward, or do you envision that there might have to be more descopes or other cost-cutting measures as we go forward? I guess where I'm going is, like Manda and I were both on the midterm review panel back in 2018 for the last decadal, and we were sort of told this was going to be a very focused and rapid mission, and clearly it's not. It's an incredibly complex and amazing mission, but it's not going to be easy to keep the costs down. So
I'll just come up here. So to your point, yes, I mean, we've all, I think, appreciate the complexity of our mission, right? And as I kind of mentioned earlier, the complexity is driven, we're not just landing and picking up a sample and bringing it back. We've built our architecture to support our mission to collect scientifically selected samples that Ken and his team have been collecting. You heard Minnie describe the diversity of the samples that we've collected through that process and will continue to collect. And that means our mission, has to be able to go and either land near the caches on the surface or to land where Perseverance ends up. So that kind of drives requirements. On top of that, we've got the black planetary protection requirements that you all understand. This is really the first time we're breaking new ground here and implementing those. So this architecture is complex. It's organizationally complex. As I mentioned, the one thing we have is we're not trying to do a lot of technology development in parallel. So we've got that. I think we are largely converging on an architecture that we're taking to PDR, and the reason we're doing the IRB is to validate that we have got solid plans. I think the thing that we're doing different on this mission, maybe that hasn't been done on previous missions, we are putting a lot of scrutiny to make sure that we understand not just the technical architecture closes, but that we understand the cost and schedule before we take it to agency confirmation. So I do have confidence that we are converging on an architecture. We do have work to do, though. We're still completing our grassroots estimates coming out of the elements, and those, as I mentioned, will get validation through independent reviews, on top of the IRB that we're bringing back. So it will get lots of scrutiny, and then before we go to confirmation, the agency will make final decisions about what we are taking forward. So I don't think I'm in a position right now to give you cost data because we're still working it through our processes.
Okay, thank you. Okay, unfortunately, we are out of time for this session because we have to turn the room around for the next town hall. So if you could join me in thanking our speakers today.